Okay, so now we've contained the blast radius of having one universal key for the whole system, and each badge gets its own key. We are operating under the assumption that an attacker cannot in some way communicate with the badge. And you know what? That actually might not be true. If the attacker were able to install a skimmer on the reader, then maybe it could sort of intercept communication with the badge. Or maybe the attacker is wearing a reader, walking around an area where they think people have badges, and if they can get close enough to a person's shirt pocket or wallet, then the badge might start the authentication process because it doesn't know, it's not near a door, it just sees that a reader is within proximity. And potentially that's harmful in the case where after the reader has authenticated the badge, even if it's sort of an attacker-controlled reader, then they can begin reading and writing from memory on the badge. So maybe they can read sector 0 and get the data back, or identify biographical information, or which doors the badge has access to, or change those sorts of values by impersonating a reader. So we took all this time to make sure that the badge could authenticate to the reader. We never thought to check to make sure that the reader could authenticate to the badge. So in exercise 4, that's what we're going to do. We're going to reach mutual authentication now, where both sides authenticate each other, and they have confidence that the badge is talking to a real reader, the reader is talking to a real badge. Now, if we try to kind of naively apply the solution we looked at in the last few exercises, technically it would work for the readers to get their own unique keys, and for the badges to sort of derive those keys. And if they sent a nonce to the reader, the reader computed the MAC and sent it back to the badge. That all would work. The problem is we would be putting another universal key on the badge, and even if it weren't the same thing as this fleet key, well, we've already sort of assumed in our model that the attacker can potentially get access to a badge and extract that key. And so we're no better off than we were before if we kind of try to apply that solution. So what we need is for the badge to get a value that it can use to verify a reader, but one that if it were to be revealed, if an attacker were to extract it, would not let them subsequently impersonate a reader. And in order to do that, we're actually going to have to lean now on asymmetric encryption. The encryption you're probably most familiar with is symmetric encryption. That's where we've got one key that's used to both do the encryption and the decryption process. Asymmetric encryption is mathematically a bit more complex, but it gives us a couple of really useful properties. In asymmetric encryption, there's not a one key, there's two, and they're very aptly named the public key and the private key. We can do encryption with asymmetric cryptography, and we can do cool things like key exchanges. The diagram here shows you the usage that we have for it, which is to create a digital signature. And very much in brief, the way digital signature works is that an entity can use their private key, which is known only to them, to sign a message. And the output of this signing process is some value, kind of like our Mac was, right? Some value, which is the digital signature of this message using the private key. The sender will give the message, the digital signature, and their public key to the receiver. And very critically, the public key can go anywhere. Anyone can know the public key. But there is the receiver now has an ability to execute a verify algorithm, and the verify algorithm can use the message and the public key to compute a value and effectively get to the same value that the digital signature had, and in so doing kind of verify that, okay, if the signature matches the one that was sent to me, then the only possible way for that to have happened is if the message was originally signed by a person with the private key. So anyone can know the public key, but as long as only the sender knows the private key, then we can sort of craft this value, craft this message that proves only the sender had the ability to send this message. And so we're going to use that to authenticate the reader. So the process now, you'll notice the top part here operates exactly the same as the previous exercise. So the badge presents its UID to the reader derives the key and sends a nonce to the badge. The badge computes the HMAC of that nonce using its device key, and the reader says, okay, yep, this is a valid badge. Next, what happens is that the badge will authenticate the reader. So the badge will send a nonce to the reader, and the reader's the kind of like Alice in this case. The reader is going to use their private key and the nonce that they got sent from the badge and compute its digital signature. ED25519 is one algorithm to compute the digital signature. So they send that digital signature to the badge. The badge now kind of is representative of Bob in this scenario. The badge, it knows the message it sent the nonce. It was flashed at build time with the reader's public key, and now it has the message. So that's all three pieces that the badge needs to then conduct the verify algorithm and check to make sure that, yes, this response I got from whoever I'm talking to could only have been computed by a device that knows the private key of the reader. And as long as you assume that, that only ever goes in valid readers, at this point, the badge can say, yep, I'm talking to an authenticated reader, and we can do our little data transmission knowing that we're talking to the proper parties on both sides. And again, very critically, the public key is truly public. So even if an attacker gets access to the badge, they can extract the badge's device key and the public reader key. There's still no way for them to impersonate a reader without that private key that they have. Okay, so that takes us into exercise 4. You're going to conduct some exercises to make sure that we understand how this process works to mutually authenticate both devices. In the red level exercises, you're going to complete the flowchart of the session.py's run function. You're going to map these steps in our sequence diagram to the functions in badge.py and reader.py, so we know kind of how these all correspond to the sequence diagram that we've looked at so far. And then you're going to implement those functions on your own in order to perform the mutual authentication. After that, I'd encourage you to take a couple of the yellow and green level exercises, try your best to answer them to kind of deepen your understanding, and then we'll move on to the second to last video.